everyone accept that? Okay, Abdul, we'll make a start. Welcome everybody to the Fleet seminar. I will let Abdul introduce himself and everything else because I am unfamiliar with Abdul and I haven't done my homework on presenting or developing an introduction for him, so I'll let him do that. But Abdul, over to you. You can lead the show from here.
All right. Thanks, Jason. My name is Abdul Hakim, and I am a last year PhD student from the University of Wollongong. And I work with David and Charlene from University of Wollongong. So really happy to present some of my work during my PhD studies at them. And right now, so my work basically focused on engineering Orient disorder at the surface of topological insulators to study their electronic properties. So this is the outline of my talk. First, I will give very brief, very short introduction and background. And I assume many of you from Fleet knows topological insulators very well. So I will mainly focus on some of my results. And I will divide my results into 4 different sections, as you can see here. And then I will finally come to a conclusion and some of my work planned for future. So pretty much everyone knows what is topology, and so basically in topology is a mathematical term which classifies different objects according to their genus number. As you can see here, in different class, basically you count the number of holes, which is called genus number, and you classify them. So the concept of topology also applies in electronic band structure of materials. And when you take the integral of a closed path or Gaussian curvature, you will get some integer number which is used to classify the topology of objects. But when you take the integral over a closed path on the barrier curvature, you will get some integer number, which is also used for classifying this band structure of materials. So there are many way of classifying band structure, like Z2 classification or some other classification as well. So we know topological insulators is very interesting type of materials, and their bulk is insulating, surface or edge has metallic conducting states due to strong spin orbit coupling. And as you can see from this illustration, so it's basically, in analogy, it looks like a chocolate wrapped in a aluminum foil where surface is conducting and bulk is insulating. But in the material is topological insulator is much more interesting than just chocolate wrapped in a aluminum foil. So the interesting part is when you cut the topological insulators, there's at the surface you will still new surface states emerges. So in my presentation, as I initially said, I will focus on engineering Orient disorder. First is it's very interesting to know that most crystals, specifically the crystals that I'm working on, like antimony telluride, bismuth telluride, or bismuth telluride, are very sensitive to ion beam. So it is very difficult to get atomic atomic. It's very difficult to image them in using this STEM. So initially, to study how disorder affects how ion beam interacts with topological insulators, I have developed a method to basically characterize the atomic structure of this sort of crystals, where we can see it's very useful. STEM beams can reveal some of the defects, some of the vacancies. So without a proper way of preparing this high quality lamella and using STEM to study their atomic level structure, it's hard to quantify how ion beam interacts with topological insulators, specifically antimatter, and how we can really quantify their structure when we irradiate it with ion beam. Basically, ion beam interacts with materials in many ways. It can cause swelling, it can cause also material removal, and I've been using focused ion beam for various reasons. And as you can see, when ion beam irradiates the surface of topological insulator, it causes amorphization. So many people struggles to get high resolution atomic scale imaging due to amorphization. So I developed a method where absolutely minimizing the ion beam amorphization. And as you can see, this amorphization or the damage level depends upon the incident angle and also the energy. So by choosing proper energies, and we can actually really fabricate high quality TM lamella, where we can study atomic structure of this metal. Here I just showed the comparison of this conventional method, which is quite useful for most of the materials, but this general method, it's not really used or suitable for very thin films or very much ion-beam sensitive crystals. So this method where I developed, it's a really reliable method for fabricating high quality lamella for STEM characterization. You can check out the details if you're interested in this work. And the main, as I said, there is a way to control the disorder by minimizing the ion beam energy and irradiating this surface with various angles. So this is just showing how we minimize the ion beam amorphization at the surface, eventually using this TM and aberration corrected system to reveal the atomic structure of this material. Here you can see this. Here right side shows the unirradiated region and left side shows the irradiated region. Even very small amount of ion beam can cause amorphization. This is actually interesting work. Basically lays the foundation for some of my future work, which you will see soon. So by this, I would like to basically show that there is a way to basically using a proper ion beam, choosing proper ion beam parameters to prepare a high quality lamella, which we can use it for as atomic scale as STEM imaging. And second part is also how we can we know this topological insulators, they have surface states, and according to some calculations, surface states usually appears as the top 3 to 5 nano depths. So what I have found is this the maintaining this crystallinity of surface states is really important when fabricating a device using focused ion beam, because focused ion beam, as we discussed before, focused ion beam is antimonoclide light is really sensitive to ion beam, so very minor amount of small amount of ion beam radiation can cause damage and amorphize the surface. And it is really interesting that there are a lot of work has been done on this focused ion beam assisted device fabrication, where people studied the people studied the transport properties along different crystal direction, and also we know when this materials reach micro nano level, they show totally different transport properties in some of the materials. So one of my in the past literature, all the device fabrication basically focused on this adopted laminar preparation method, where this device basically all the surface basically irradiated with ion beam. This method of device fabrication not really useful for some of the ion beam sensitive crystals such as antimonoclide. So here you can see before device before or microstructure fabrication or device fabrication, electron backscatter diffraction is really useful method to basically check the crystallinity of the sample or align them to a specific crystal direction, and even it can be used for screening crystal quality. So as you can see here, we have some of the regions is amorphized, where irradiated with intentionally irradiated with iron. It doesn't show any Kikuchi bands, which is because of amorphous nature of this crystal surface here. And when it's crystalline, it shows very strong Kikuchi band, and each Kikuchi band here actually reflected from specific crystal plane, which is very useful for when we fabricate devices, which is very useful for aligning them to specific direction and study their transport properties along specific crystallographic orientation. So in the method I developed is basically avoids excess ion beam irradiation of the surface, and in my case I found it's very useful method. Initially we use ion beam to basically make a trench around any geometry, like it can be circular disc shape or it can be a rectangle shape, and this way still when you irradiate the surface of the material, you still form some sort of amorphization, but you can still use this nano manipulator. You can remove surface by controlled fracturing, then you can lift out the same structure again, which is not radiated with ion beam at all. So that means that both surface of this tiny microstructures is crystalline, and it really represents the true structure of this material, and this transport properties is really represents materials itself. So here basically shows how I fabricated device. I will not focus much on this. And there are some failures during device fabrication, and this is due to applying high ion beam current and sometimes overheating. We did some in-situ heating of these devices. So in some of the device initially fabricated, it shows pretty bad transport properties because the surface is amorphized. It doesn't really represent the true atomic structure of this material. And based on the method I developed, so we can fabricate different geometries of devices on different sort of chips. As you can see here, we have this heating chip or chips, or we can use this biasing chip. And after fabricating device, we did some transport measurements and some heat treatment measurements. Initially, when the device is fabricated using the method I described initially, so even after the device fabricated, we could still clearly see strong Kikuchi patterns coming from the surface, which tells it is crystalline. It's not been amorphized, and also this unit cell view tells us it's along C-axis. So when we intentionally amorphize the surface here with certain ion beam parameters, we cause amorphization, which is not indexed on this Euler or phase color image, even in band contrast. This is amorphized, and upon heat treatment at 400 degrees Celsius for half an hour, we could reverse the crystallinity in situ, which is very useful for some of our future studies, which we'll see soon. And also, there is another way of even further reducing the ion beam damage during device fabrication. First, I do the exfoliation, and then in the microscope, I look for desired thickness of sample, and I can align this sample. I can align the sample in specific crystallographic orientation using EBSD. And in this case, this sample surface, only the edges is irradiated with ion beam, but the front and back surface is not really amorphized. And we can see some of our transport measurements on these tiny structures. It's very typical of this crystalline bulk crystal, where it shows strong Shubin-House oscillation. And some of you might wonder why you want to fabricate devices. It will be very useful for some of my future studies I will be discussing soon. So in the initial device fabrication, as I showed very early, when the surface of this antimetalloid is amorphized, we don't see any oscillation, and we don't see this transport properties. It shows totally different transport properties. So as you can see, when the surface is, this is the device where the surface is amorphized. And this is basically some strategy where how I avoided surface amorphization and created this transport devices with without amorphizing the surface of antimoney chloride. So the basic idea is there is a way to fabricate devices, and we can take the advantage of electron backscatter diffraction. We can align this crystal to a certain crystallographic direction, and we can study the if any, we can study the anisotrophic transport properties with respect to different crystal direction. And again, I come to one of my most interesting results. In initial in early, I showed you how we can avoid amorphization or avoid disordering, introduce disordering at the surface of antimoney cloud. But here I would like to discuss how we can introduce disorder in a controlled manner to engineer topological states at the surface of antimoney chloride. We know between this when this topological and at the we know this topological insulator and trivial insulators, and at the boundary the gap must close. This is very interesting clue for us to engineer surface or edge states using using a method where we can really create phase change in some of the crystals. The way how we did in our studies is, can we use this ion beam to introduce disorder at the surface of crystal where crystalline region is it's topological, but when you introduce a phase change, and then the region will transition from topological to non-topological. And there are so many theoretical studies in recent few years, and most of them studying the effect of strong disorder, and even some of the papers discussing the existence of amorphous topological insulators. So our studies is one of, I would say, first to at least to rule out what is the fate of topological states when under the strong disorder or amorphization. So when this antimoney chloride is crystalline, we can see nice a clear band gap in the bulk, and we could see this surface states crossing the bulk band gap. But when it's disordered, we could see this disappearance of this surface states, which is basically basis for our work to engineer surface or edge states wherever we want at the surface of antimoney chloride. Now, as I showed very early, I did a lot of work using focused ion beam, using TEM STEM to study the atomic structure of this crystalline material, to really not introduce disorder during this sample preparation, rather to reveal the real atomic structure. As you can see, when it's irradiated with different ion beam energy and different ion beam fluence, we could introduce disorder or amorphization, where you can kind of clearly see this transition between amorphous and crystalline structure. This transition usually happens within 2 nanometers. So that means we can, using ion beam, we can create really sharp interface or structures. So there's a lot of studies that I have conducted to study what is the effect of different ion beam fluence energy, and using using EBSD mapping, we can clearly see there's some transition when, as we gradually increase the ion beam fluence, we could create amorphization. And this, using this Kikuchi band map, you can clearly see at certain level of ion beam fluence, the surface of antimetalloid is amorphized. And this amorphization, basically, as we see previously, can cause phase transition, which is very useful to engineer surface and edge states. And this is the critical fluence which causes the amorphization of this antimetalloid, which is only 1/3 of the fluence that can create amorphization in silicon. That means this sort of metals is really ion beam sensitive. And so we did a very systematic study. And also we used conducting atomic force microscopy to study the surface and conductivity of this irradiated surface with different ion fluences. As you can see, those regions appear in black, actually irradiated with very high ion fluence, and which is amorphized, and it also shows less conductivity on this CAFM map. And also here, this is a topography image, which basically shows ion beam. Actually, also when you use excess amount of ion, it can actually start to remove your material. So there is a very there's a certain point where we can control the ion beam energy and amount of ion dose to amorphize the sample but not remove the material. And there's also, as you can see here, there's certain relationship between this ion dose and the amorphization. Initially, we see some swelling effect in this material, then this material start removed, and when it's amorphized, we see some significant decrease in the current. And when we did, the most interesting part is even at room temperature, we see some sort of high conductivity at the edges between crystalline and amorphous region. So some of our previous results show that when we did transport studies on this bulk sample, even the surface is amorphized, but the bulk crystal still shows, because of this leakage current, still shows even its top, because the ion beam only can, depending upon the ion beam energy, it can amorphize top 10 to 50 nanometers region. And this is, when you study the transport properties of this bulk crystal, it is still identical to crystalline material. But when you fabricate devices, when you reduce the thickness of your crystal, and that to really study the effect of amorphization or disorder, then this device fabrication come into handy, and it's really useful. As you can see, when the sample surface is amorphized, we could see the total different temperature response of this material, and also the change in the resistance in the order of magnitude. And as you can see, that there is very high current at the border of amorphous and crystalline surface. So that's really interesting. As I previously said, when you amorphize the surface of bulk crystal, it's really hard to totally isolate the transport properties coming from the crystalline underneath the amorphous few 10 nanometers region. And also, so we did some transport studies on this thin films where this crystalline antimaterial shows weekend localization, which is a signature of topological insulators. But when it's amorphized, the resistance is in the range of mega ohm, which is also the the resistance increases when the temperature decreases, which is very similar to what we saw before when we fabricated the device. When the device surface is amorphous, and we see the similar trend in the case of this amorphous materials. But when this device surface is crystalline, we see this we see the signature of this topological insulators transport. And some of the simulation done by our collaborator from RMIT and also from my supervisor, it clearly shows when this amorphous, when antimaterial is amorphous, there is a gap in the bulk and surface. But when it's crystalline, we can clearly see this direct surface states. And this is a real space Hamiltonian model done by some of our collaborators from RMIT, and clearly shows when this crystalline material is not amorphized without any disorder, it clearly shows surface states at the surfaces between the crystal and the vacuum boundary. As we gradually increase the disorder strength or induce amorphization, this surface states gradually disappears, and even eventually under much more stronger disorder strength, it wraps around the boundary between amorphous and crystalline region. That's really interesting. So that means basically using ion beam, we can engineer surface and edge states on the surface of antimaterial light, which is really useful for building electron barrier or building high conducting channels. Such as in this illustration, as we show, when this region shows amorphous region, this region shows crystalline region. At the boundary of amorphous and crystalline region, we have 1D edge states. At the surface, we have 2D surface states. And that means using this ion beam, we can really engineer edge and surface states anywhere we want. So this also concludes that when this antimaterial is crystalline, it's topological insulators, but when it's amorphized and its topological environment changes from Z1 to Z0, so that means that Z2 number changes from 1 to 0. That means there's phase transition, and at the surface of this amorphous and crystal metal, we must have edge or surface this, as we discussed very early. And if you're interested in this work, recently we published our work in Nature Communication. Please check out our paper. And the last one section of my result is still not complete, but I'd like to introduce. Previously, what I have discussed is introduce disorder in the surface of antimaterial, but we know when we can also introduce another form of order using magnetic ion-beam doping, and this is very useful where we magnetic ion-beam in topological insulators is really interesting due to quantum anomalous Hall effect, which is very useful for sputonic and some other electronic device application. Here, we did some study on this magnetic a manganese doped antimonoclide. Here I just did some study to confirm that manganese is doped on the surface of antimonoclide, which we use ion-beam accelerator at Anasto, and some of my initial results shows that at very low temperatures, around less than 100 K, we see some ferromagnetic feature, and this is really useful. And however, when I did some transport properties, although the surface of this crystal due to ion beam, it's amorphized, but we still, as I said before, we still see this article, which is typical to crystalline sample. So that basically caused due to this current leakage, which is still this transport produce mainly coming from the bulk crystalline material beneath the amorphous region. That's one of the reasons why I, in some of my studies, focused on this device fabrication using focus ion beam. And as you can see, this microstructure here clearly shows when this antimony telluride doped with manganese at this energy and with this influence, we could clearly see up to 65 nanometer of amorphous region, and right below this region it's still crystalline, but the initial transport still shows the characteristics of crystalline sample due to current leakage. So so by introducing magnetic ion, we can introduce magnetic order, another form of order in topological insulators, which is also useful for patterning the surface of topological insulators. We did some very initial patterning using grid, where this shows grid of specific dimension, and we placed this grid on the top of antimony telluride, then irradiated the surface of antimony telluride with manganese ion beam. And we can clearly, from this secondary electron image, we can clearly see that this region is irradiated. This rectangular patches are irradiated with manganese, and this region are not irradiated. So this region is crystalline, and this region is amorphous. And also this region is implanted with magnetic ions. So as you previously seen from our initial we have some results that there's some, at very low temperature, we see some ferromagnetic ordering, so which is really useful, but bulk transport properties is not really helping us to study what is really happening. So when you look at this EDS image, you can clearly see this region where this patch irradiated with manganese. And so this work still in progress, and I still plan to fabricate devices at different interface, let's say between magnetic and the crystalline region, and to build different devices to study what is their effect, and possibly can we see any quantum anomalous effect. So by this end, I would like to conclude my talk by this is the one of our main point is that at least we ruled out what is the effect of strong disorder or amorphization in the antimoney telluride, and strong disorder or amorphization basically cause quantum transition, so which causes topological to non-topological transition. And there are so many studies showing existence of surface states even under very strong disorder, or the existence of amorphous topological insulators, which is still most of them in theory. So it is really interesting to study other types of materials. So is this topological transition induced through this disordering or amorphization universal to all topological insulators, or just some of this, like antimoney telluride? Because some recent publication shows even amorphous bismuth selenide shows topological nature, which is quite contrary to our studies here. So if you're interested in some of our work, please check out my publications. And by then, I would like to thank to our my supervisors and all our collaborators from NS2, RMIT, and UNSW and Monash. Thank you so much, and I'm open to any questions.
If there's any questions, guys, just unmute yourselves and ask away. One comment from Goal there. That's a big list of people you're working with, Abdul.
Yeah, I got a lot of help during my PhD, so I'd like to really thank everyone who helped me during this. And anyone, if you're interested in collaborating, please get in touch with myself or my supervisor. Thank you.
I have a question.
Yep.
Abdul, so can you hear me?
Yes.
Very nice. So you mentioned in the future you want to do more fabrication, doping it with magnetic materials and using antimoney telluride. And antimoney telluride seems like to be really nice, easy to grow, easier than other TIs to fabricate as well. But are you planning or thinking to use any other topological insulators, any other materials in future?
At the moment, I had some initial results, still mainly focused on antimoney telluride, but of course, I'm open to some other materials. That is interesting. But my work mainly focused on antimoney telluride.
For the time being.
From as you can see, from various level of microstructural characterization to advanced fabrication and to surface engineering and some magnetic.
Yeah, it would be nice to try bismuth selenide and bismuth telluride, maybe bismuth selenide, as they reported different.
Yes, I think this is also very interesting because very recent experimental look. Yeah. As far as I know, first experimental look shows this topological surface states. Even this bismuth selenide is amorphous, but I'm kind of skeptical to their results. But it's interesting to do some follow-up studies.
Yeah. Well done. Very nice.
Thank you.
Hey, hey, thank you, Abdurrahim. Can you hear me?
Yep.
Yeah. Very nice work. I also have a question. Just when you use the iron beam to change the crystalline structure into the amorphous, what is the maximum like thickness you can impact it?
Oh, it depends upon the ion-beam energy used. So as you can see here, right? When you use different ion-beam energy, the impacted region, when you increase the energy, impacted region gradually increases.
Okay.
Even if you use very high energy in the range of mega, what I think you can probably create.
Okay, so so does it mean that if you have this sample, for example, on the substrate with like a 5 to 10 nanometers, you can change the materials within like through the whole thickness into...
Oh yeah. I think few 10 nanometers or less than 100 nanometers is quite easy with low energy ion beams. Yes.
Have you tried this in other materials other than this one?
Not yet. I
Okay.
mainly focus on antimetalloid.
Okay. Okay, thank you.
Any more questions from anyone? No. Oh, Abdul, thank you very much for that presentation. Even the non-physicist like me picks up little bits from these sorts of things, so it's been great. And that will say goodbye to everyone, and thanks very much, Abdul.
Thank you.